Now let us discuss the chapter rational numbers. So what are rational numbers? Before going to start rational numbers, we must have the previous knowledge regarding natural numbers, whole numbers and integers. So first, what are natural numbers? So what are the numbers used to count the things? Naturally we use 1, 2, 3, 4 and so on. So these numbers are called natural numbers. The set of natural numbers is denoted by n. Is equals to 1, 2, 3, 4 and so on. The smallest natural number is 1, but there is no largest natural number. But are these numbers sufficient to solve the problems, to solve some equations? See, for example, an equation x plus 3 equals to 9 is there. So what is the value of x satisfying this equation? Obviously 6. If you put x value 6, this equation will be satisfied. So we can take any natural number to satisfy some equations. Now let us take another natural number, another equation like x plus 16 equals to 16. So what is the value of x to satisfy this equation? Can you take any natural number to satisfy this equation? Obviously no. If you substitute x value 1, then 1 plus 16 is 17. So these natural numbers are not sufficient. So we need to extend our numbers. So then if you put 0 in the set of natural numbers, this will become whole numbers. So then whole numbers denoted by w, this equals to 0, 1, 2, 3 and so on. The smallest whole number is 0, but there is no largest whole number. Next, let us take another equation like x plus 7 equals to 2. If you take another equation like x plus 7 equals to 2, now what is the value of x to satisfy this equation? If you take x value 0, then 0 plus 7 equals to 7, but here RHS is 2. So there is no whole number to satisfy this equation, but here actually the x value is negative number. So we have to include the negative numbers in the set of whole numbers. Then we get integers denoted by z. Z is the collection of all negative numbers, 0 and positive numbers. So minus 3, minus 2, minus 1, 0, 1, 2 and so on. So there is no smallest integer and there is no largest integer. Let us take another equation 2x equals to 3. Now what is the integer to satisfy this equation? If we substitute any value of x, the LHS is not equal to RHS. Actually if you solve this equation, then x equals to 3 by 2. This is a fraction, but there is no fraction in the set of integers. So we need to extend our integers. Then the fractions together with integers become rational numbers denoted by q. All the rational numbers will be in the form p by q, comma p comma q belongs to integers and the denominator q is not equals to 0. So this is a set of rational numbers. Every rational number in the form p by q, p and q belongs to z and the denominator should not be 0. For example, 2 by 3 is there. 2 by 3 is a fraction as well as a rational number. Here 2 and 3 belong to the set of integers. Every rational number in the form p by q, here p and q belongs to z and the denominator q should not be 0. If you take 2 by 3, it is a rational number because 2 and 3 belongs to z and the denominator is not equal to 0. If you take 5, so even 5 also a rational number. How 5 is a rational number? 5 can be written as 5 by 1. So here p and q means 5 comma 1 belong to integers and the denominator is not equal to 0. Now let us discuss the properties of rational numbers. The first property is closure property, the second property is commutative property, the third one is associative property and the next one is distributive property. So let us discuss the first one, closure property, and this we will discuss in natural numbers under these 4 binary operations like addition, subtraction, multiplication and division. So first let us discuss in addition. What is the sum of any two natural numbers? 2 is a natural number and 3 is also a natural number. What is their sum? 2 plus 3 equals to 5. So the sum of two natural numbers is also a natural number. So the closure property is satisfied under addition in the set of natural numbers. So natural numbers are closed under addition. Like if A and B are any two natural numbers, then A plus B is also natural number. So natural numbers are closed under addition. Now let us see under subtraction. Now 2 and 3 are any two natural numbers. What is the difference? 2 minus 3 equals to minus 1. But here minus 1 is not a natural number. So if A and B are any two natural numbers, then their difference may not be a natural number. So natural numbers are not closed under subtraction. So here natural numbers are not closed under subtraction. Now let us see third one, multiplication. 3 and 4 are any two natural numbers. What is their product? Like 3 into 4 equals to 12. Here 3 and 4 are any two natural numbers. Their product 12 also a natural number. So the product of any two natural numbers is again a natural number. So the closure property is satisfied in natural numbers under multiplication. So here if A and B are any two natural numbers, then their product A into B also a natural number. So natural numbers are closed under multiplication. Now let us discuss the closure property under division. Here 3 and 4 are any two natural numbers. Now what is their quotient? 3 divided by 4. This equals to 3 by 4, which equals to 0.75. But this is not a natural number. The quotient of any two natural numbers may not be a natural number. So the closure property is not satisfied in the natural numbers under division. So natural numbers are not closed under division. So the closure property is satisfied under addition and under multiplication in the set of natural numbers. And the closure property is not satisfied under subtraction and division in the set of natural numbers. Now let us discuss the closure property in the set of whole numbers under these four operations as addition, subtraction, multiplication and division. So if you take any two whole numbers like 0 and 4 or any two whole numbers, what is their sum? 0 plus 4, which is equals to 4. So this is also whole number. The sum of any two whole numbers is again a whole number. So if A and B are any two whole numbers, their sum A plus B also whole number. So closure property is satisfied in the whole numbers under addition. So whole numbers are closed under addition. Now let us check the same closure property in the set of whole numbers under subtraction. Now here 0 and 4 are any two whole numbers. Then what is the difference? 0 minus 4, which is equals to minus 4. But minus 4 is not a whole number. Actually it is an integer. So the difference of any two whole numbers may not be a whole number. So if A and B are any two whole numbers, then the difference A minus B may not be a whole number. So whole numbers are not closed under subtraction. Now let us check the same property under multiplication. Like 0 and 5 are any two whole numbers. Now what is their product? 0 into 5, which equals to 0. 0 is also a whole number. The product of any two whole numbers is again a whole number. So closure property is satisfied under multiplication. If A and B are any two whole numbers, then their product A into B also whole number. So the closure property is satisfied under multiplication. So whole numbers are closed under multiplication. Now let us check the same thing in division. Now let us check the closure property under division. If here 3 and 12 are any two whole numbers. Now let us find their quotient. 3 divided by 12, which is equals to 3 by 12. 3 1s are 3 4s are, which is equals to 1 by 4. Here 1 by 4 is not a whole number, means the quotient of any two whole numbers may not be a whole number. So if A and B are any two whole numbers, their quotient A divided by B may not be a whole number. So the closure property is not satisfied under division, means whole numbers are not closed under division.